Good morning. I will be talking about, I changed my title slightly. I will be talking about persistent nanohertz gravitational astronomy. Let me introduce myself. I am approximate Gopakumar in comparison to the real Gopakumar you heard early. I am from the headquarters. That simply means that it's from TIFR Mumbai. That's the form I fill to attend the meeting. I am a proud member of Indian Pulsar Timing Array, and we are an integral part of uh, International Pulsar Timing Array. I also spent some time in Seoul National University. I'm actually talking from Shanghai Observatory. Sorry for not able to come over there. Um, Bruce kind of briefly mentioned about it. It took a millennium for multi-wavelength electromagnetic astronomy to happen. This is the famous 1054 event that Chinese astronomer Shen Kuo and his colleagues observed, and now we have seen this in radio, X-rays, infrared, and gamma rays. And I'm fairly convinced that multi-band gravitational astronomy should happen in decades. And also, the universe, this is the music we are trying to follow, right? Will be in two voices, persistent and transient, fairly similar to the way electromagnetic astronomy matured via GRBs and CMBR when we were doing PhDs back in 90s. So we need millisecond pulsars and supermassive binary black hole for persistent nanohertz gravitational astronomy in the coming years. And this is the cartoon. I apologize. I've been making these slides in PowerPoint in a hurry, so the credits may not be there. I don't want to use VPN while giving the talk. That's the Okay, so pulsar timing array, already Bruce mentioned that this is for the nanohertz gravitational astronomy. So if you're looking at the astrophysical gravitational spectrum, that essentially goes from nano to hectohertz. And this is the beautiful plot where you actually see this. So the gravitational waves that we are hoping to detect firmly in the coming years are in nanohertz, and the effective strain is of the order of 10 raised to minus 15. That's essentially 1,000,000 times stronger than what LIGO is seeing. But as Bruce mentioned this, we have to go after the correlation, cross-correlate that ensures that we are looking for things which are at 10 raised to minus 30. That's the difficulty part too. But the square kilometer array that's already under construction, where both China and India are going to play a significant role, is going to revolutionize nanohertz gravitational astronomy. And this plot is essentially for the energy density in gravitational waves divided by what's required to close the universe. That's again Bruce kind of alluded to. It's a dimensionless quantity as a function of frequency. You can see that when the SKA fully matured, that dimensional ratio will improve from something like 10 raised to minus 10 8 these days to minus 14, which is comparable to what the previous speaker talked about, possibility of Einstein telescope and LISA and other big planned observatories of the coming decades. So, and the good thing about is that SKA-PTA should be operational by early 2030s. And for the time being, we have International Pulsar Timing Array. So this is it's the way to describe this is a consortium of consortia. So we have our American colleagues via the Nanograv, which uses the best radio telescopes they have at their hand that include GBT, Arecibo, VLA, CHIME, and then our European colleagues using the GEN, Effelsberg, and the venerated Lowell, Nancy, WSRT, SRT. And then we have exciting Meerkat radio telescope being adopted into the MPTA. And we have good presence in IPTA with our own upgraded giant meter wave radio telescope in Indian Pulsar Timing Array. And the Parkes uses the Murray-Young in Australia. And then the CPTA, the Chinese Pulsar Timing Array, uses the biggest radio telescope of all. That's the FAST. And in the coming year, there will be a bunch of GBT class telescope joining the effort. So it looks good. And the IPTS should be able to inaugurate the era of nanohertz gravitational astronomy in the coming years. And what are the sources? Bruce briefly mentioned about it. We expected to see a stochastic gravitational wave background from supermassive binary black hole. Individual supermassive binary black holes are also going to be possible. These are individual, isolated from the background, and the burst with memory events. You can see that what we need are the timing residuals, the expected time of arrival, and what we can predict. And if we can bring them into tens of nanoseconds, things will happen, and the data span will be decades. And so this is how in the characteristics train you look like. So you have a background, and then you will start seeing individual resolvable supermassive binary black holes. And then, of course, if there are supermassive binary black hole merging happening at, up to a gigaparsec or more, you should be able to see the memory of that too. And there are other events which can create that. I'm again restricting to astrophysical sources. Theoreticians present in the audience will have many, many more sources for nanohertz gravitational wave background. Why are we interested in all this? This is the astrophysical scenario we are trying to kind of explore. You have massive galaxies merging, that we already seen with Hubble and JWST and many other electromagnetic observatories. We expect the supermassive binary black hole to form a pair, and hopefully this final parsec problem created by Martin Rees and his collaborator are theoreticians' problem, and we have a reason to believe that. And when they reach milliparsec separations, they will emit nanohertz gravitational wave. They will eventually merge within the Hubble radius and then Hubble time, and then recoiling supermassive black hole, which we can actually look for in spectroscopic surveys like DESI and other. So this is the scenario we would like to know in detail. And why a stochastic background is expected? Well, the game is that, as you already heard, that the timeline of PTA are years. So our frequency sensitivity, which is essentially inverse of that observational span, and then we can ask the question, how many such sources are expected in that binary that frequency interval? You can actually compute that in a fairly straightforward manner. Delta n can be written as dn over df times df. You do that again, dn over dt times df by dt times del f. df by dt already LIGO measured. Before that, Joe, with binary pulsars are measured, so we know exactly what df by dt is. So you can rewrite that, and this is the formula you get. And if you imagine that every galaxy merges at least once in a year in its entire lifetime, in its entire lifetime, and then we can and then associated black holes also merge, then you get the number of sources in that frequency bin of 10 nanohertz or something are going to be, a million minimum. There are lots of uncertainty here, but still. So this is why we expect this to be a background. Is characterized by an amplitude and a frequency exponent alpha, which of course we need to demonstrate that it's an array. So we actually have to cross-correlate timing residuals from many pulsar pairs and see whether we can see this, Hellingson-Downs correlation curve, which is not exactly quadrupolar as eloquently explained by Bruce in many of his beautiful articles. Why this excitement? In the last few years ago, Nanograv, EPTA in collaboration with INPTA, CPTA, PPTA, and MPTA have found spatial correlations at varying sigmas 2 to 4 in our independent but coordinated efforts. And that's exciting. That's what now we are combining our resources, pooling the data and analysis algorithms and all that. The results are expected in the coming years. And why this is exciting from an astrophysical perspective? Well, I'm again plotting the characteristic strain as a function of the frequency. The dotted line is assuming that all the binary black holes will merge along, circular orbit like your, stellar mass black hole binaries of the LIGO, Virgo, Kagra consortium. But if they are not, and there are other effects like eccentricity, stellar scattering, viscous disk, and environmental effects, then things are going to be different. And we can actually probe with, frequency bins of 30 or something, this frequency bin in the coming years, and actually can tell you how that speculated final parsec problem is overcome astrophysically. And but exciting, as I pointed out, SKA era PTA, within few years of observation of operation, SKA should be able to reaffirm IPTS Hellings and Downs curve and other discoveries, probe small angular scale deviation from isotropy, and look for individual binaries. So this is all based on a recent, the SKA, the PTA chapter of the SKA, which are being written. So I can't share the details here. So these are going to assume we are going to time around 200 southern millisecond pulsars for something like 18 hours once in a few weeks using SKA and narrowband timing. We are not even going into the broadband timing that some of the colleagues are doing. So the hope is that, and the estimates suggest that within a decade, SKA-PTA should be able to detect roughly a dozen individual supermassive binary black hole. And this is where some of the in-PTA colleagues, my younger colleagues, are going to be, their efforts are going to be relevant. This is the first talk till tomorrow of Bruce Group, Abhimanyu. He has been developing this algorithm to look for, individual supermassive binary black hole. And they actually applied this in nanograph data while they were postdocing. This is an effort led by, driven by Lankeshwar Day and Abhimanyu. And so that's kind of opened up the possibility that we should be able to speculate and prepare for the era of persistent multi-messenger gravitational astronomy in 2030. Let me explain what I meant by that. It's essentially 170817, but the electromagnetic and gravitational waves are going to be persistent, for decades. That's because many of these binaries are expected to be in, active galactic nuclei that we can monitor in a number of electromagnetic windows. So reason for that is something I have been working in collaboration with Professor Maury Voltanen and his colleagues like Harry Leto, Lankeshwar Day, and others. We suspect that this OJ287, it's a very unique blazar. We suspect that this actually harbors a supermassive binary black hole within roughly orbital period of 12 years. The reason is that we can actually predict, and on the top of that, we think there's a companion which actually, passes through the accretion disk of the primary, which gives you that flares which I showed as this plot, and we actually can predict those flares using general relativistic simulations, and we have been doing that for the last 20 years or so, making observation at the predicted.
Yeah, you have 2 minutes.
Sure, this will be done. And so anyway, but it's expected that the gravitational waves from such sources should be picked up, and this is the work by D. Lee. That's if you haven't seen me, that's me with D and Dan. So people speculated that OJ287 is a very isolated case. That's actually not the case. The Blanford colleagues are actually arguing Blake ITKS 2131 is actually a supermassive binary black hole emitting nano-Hz gravitational wave, more tighter than OJ287. The reason is that we need decades of data, and that's the expected way of things. And I heard recently observations of this source in his teenage years, and one of the former student, one of the students of my collaboration, Avinash, who's actually from Bangalore, who's actually with Bruce Group right now, actually constrain orbital eccentricity of this event. So it looks promising. And so the game is that there will be many potential supermassive binary black hole candidates with orbital periods up to decades that we may be able to obtain. And so for that, we need to look for their electromagnetic and maybe even neutrinos. Remember the Texas event, which happened in 2017, is associated with the blazar. So this has a revolutionary science deliverables, because these are happening at cosmological distances and we have persistent signals, electromagnetic, gravitational, even neutrino. So, and of course, there's another event which is burst with memory. This has been also developed in our group. This is essentially hyperbolic captures. That's possible. We will see. And well, I'm able to, this is one of many contributions of IPTA from NPTA. And of course, I'm able to, give you this lecture thanks to Govind Surhud, who created NPTA, GMRT, therefore the NPTA. And it's such a visionary that back in 91, when he was beginning to construct GMRT, he speculated that this will be used for pulsar timing array purposes. And that's impressive because Dan actually talked about PTA just a year ago. So we are trying to create this pan-Asian efforts, which will be critical for persistent multi-messenger gravitational astronomy. And I've been very grateful to my colleagues in mainland, in other places, helping me to do that. And again, we will hear from Alvin, who's actually driving LISA Asia efforts. And the person who's actually driving this is also with Bruce, that's Reggie out there. So thank you very much. I'm sorry if I cross my stipulated time. I will be very happy to take questions. Thank you.
Thank you, Gopu. Yeah, there are a couple of questions here.
Sure. I can't hear, but you may have to translate.
Yeah. Hello, can you hear me?
Yes, I can clearly.
Hi,
I can
Gopu.
hear you clearly.
So,
Yeah, hi. May I know who's speaking?
This is Sanjit.
Hi, Sanjit. Good to hear you.
So I have been asking various people about the, what it will take to take the pulsar timing array's present compelling evidence to a detection. I understand that it is fairly complicated and so on. But on the other hand, pulsar timing array, I guess, collaborations predict that 10 supermassive black holes will be detected. Individual ones will be detected. So how does it go? Like, how can you make this prediction, but not give an idea about what it will take to make the evidence to a detection?
We already have evidence of a background, right? With a correlation varying degrees up to 4, right? I think you have seen those papers a couple of years ago. So now we are pooling our resources. This is the IPTA DR3. The result should be out there in the coming years. I am in the steering committee, but I can't share more details than that. So that hopefully, again, I'm not going to predict the future. I have no saying. Hopefully, we will have the Phi Sigma detection, whether trying to characterize whether this is astrophysical or not, and all that will happen in those years. But 2030 is still quite far away, right? So that's the kind when SKA comes along. And this 10 thing we are talking about with SKA, and the idea is fairly straightforward because individual pulsar residues will be affected by the intrinsic noise, which we will be able to control, plus those induced by a background. But when the individual signals we think we can, that also depends on the pulsar distances, right? It's not just the Earth term, pulsar term. Then they pick up an SNR of 3 or 4, we can actually remove them. There are techniques being developed, and there are papers also written. So that's a hope. Again, it's like of course, it's somewhat similar to what the previous speaker talked about, right? I mean, third generation operational by next decade.
No. My point was that if this can be done, so simply for the individual sources, why it cannot be done or estimated for the present stochastic background, like how a scaling relation, which would tell us that how much extra data or what sort of.
Yeah. So again, IPT DR3 should be able to get that 5 sigma under control. Is that what you're looking for?
No. I was saying that the scaling relation, like how much
Sure.
data or what kind of sensitivity does it take to make a detection? If
so this is
like
what
you are doing for the individual ones.
Yeah.
For example, you have like 8 years data, 10 years data. Okay, you may need 15 years data to do it. These kind of relations are not.
Yeah, so there's already scaling relation. Again, I can share those things. I mean, it will take a bit more detail on our lecture or something like that. And I'm also not the expert. Yeah, so the expected thing, for example, with the mean time and CPTA, right? They have very short duration, right? They are essentially data long, and they are reaching the sensitivity of nanograph on many aspects. Of course, the number of frequency bins are small because their data span is smaller. Does that make sense? Sanjeet?
Thank you for that talk. I wanted to make a comment about this. So
sure.
Right now in searches for an isotropic stochastic background, the model contains only 2 free parameters, an amplitude and slope.
Yeah,
and these have not yet been measured with 5 sigma confidence, okay?
No.
Now, suppose you told me that you knew that the deity had told you that the universe contains a single continuous gravitational wave source at these frequencies and no other sources. Then you'd say, okay, suppose I want to determine the sky location, 2 parameters, the frequency, 3rd parameter, the amplitude, 4th parameter, 4 numbers. You wouldn't yet have enough information to determine 4 numbers. We can't even determine 2 numbers. You couldn't determine 4 numbers with any kind of precision. Now, if you tell me the universe contains 9 such sources, each with its own sky location and so on, now we're up to 36 numbers. So there is not currently enough information yet to even confidently determine 2 numbers. There's certainly not enough information to determine, many more than that. So what's being discussed here is I think, relatively far in the future, not present.
Yeah. So thank you.
That's my
point
of view.
Yeah, I agree. So this is all the 10 thing I'm talking about is SK. This is going to come in the SK chapter.
Gopu, let's move on. There is one quick question. Okay?
Yeah, it's already.
Okay, it's already done. Gopu, wait for the discussion.
Sure. I'm online.
The break. So we are going to have more questions.